latch and flip flop.
Okay.
So,
Yeah.
so I was asked that here,
Yes. Yes.
these eight are all the flip flop and latches.
Yes. Yes. Correct. Correct.
So, sir, by looking at this, how can we know that which is the latch or flip flop and which is only the flip flop? Can
Yeah. Can you expand it more? Can you zoom it in more? Yeah. 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 So yeah, put here. So yeah, you can see this type is flip flop and latch.
that is it, but in above it is only showing FF
It's this is like only for flip flop.
Yes, sir, rest all are like here it is register in it, and
Uh,
above that it is also FF in it. I can't
okay.
find any FF or flop, FF or latch anymore type. Like that one I found, but
No, no.
not
One thing what we can do, like what we need to do, you can see certain. You put it onto that. You put it onto this one. Yeah. So you can see this CLB LM. So that site and that title. What you need to do, you need to download the data set. From there, you got the site and title, right? So from there, you need to check it. I guess this is the best way, right?
yes, sir.
Yeah, yeah. But this is same, right? This is working as a flip flop, right? And go down the latch. The latch implementation. Yeah.
Is uh, the latch.
It's working as a latch, right? So you have simulated it, right? Yeah, yeah, yeah. Okay. Fine, it. But yeah, so I think better to refer to datasheet to get to know which component because everyone will be numbered, right? So better to refer in datasheet. So datasheet will have the exact this thing. Is it fine? Yeah. So what you do, you let's say you create 4 latch and 4 flip flops. You see how it will be implemented.
Yes, sir. Thank you.
Yeah, 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 yeah. You can try that. Yeah, great. Yeah, nice. Okay. So
Sir,
yeah, yeah. Please, sir.
sir, in this FPGA, when we're implementing the design and the
Mhm.
netlist you're showing, no, which is a
Yeah,
flip flop and which is a circuit.
correct,
So
correct.
I was trying for that. So
Yeah.
after I get the design, I was unable to miss. We are selecting in the left hand side panel, and then automatically in the
Yes, yes, yes,
FPGA
yes.
certain part is selected.
Correct,
I was
correct, sir.
trying
Yeah.
that, but I was unable to select. Can you just show for one
Yeah,
second how to
yeah,
select the
yes,
things?
yes, sir. Sir, can you share your screen? I can show it in real time.
So presently, I'm logging through mobile phone, sir.
Okay,
I'm
okay,
on
fine. So,
journey.
okay, no problem, no problem. So now in the next lab, I will tell you the steps. Can you can track that steps. If any doubt, you let me know. Yeah, yeah. We'll
Okay.
show you like I will show you step by step how to select it. Right? Okay.
No,
Sir,
I mean to say that suppose an half header is there, you
Yeah.
designed it, everything is
Yeah.
ready, code is simulation is over. Now your
Correct.
implementation,
I
if
want
you
to see.
select the variables, it will show in the FPGA which part is selected.
You
It
have
was
to
showing
select
no in
a.
the last.
Yes, yes. You have to select a netlist. In
So how
netlist,
to
you have
select
to
that
select.
one then?
Yes, yes, yes. That I will take. That I will take into account, sir.
Okay, so okay, thank you.
Okay, okay. Fine, fine.
sir,
Yes, yes. Abhinav, yeah.
sir, after implementing the device we are seeing, so that
Hmm.
is in real hardware. That layout and this layout are both same, like
Yes,
exactly the.
exactly the same. That is the pictorial representation of what will be inside the FPGA. So same thing will be kind of like same. This is how the routing will be done.
So
So,
if design runs in it, so I can be 100% sure that in the real hardware it will run definitely.
correct, correct. So, like if you see, like let's say for a smaller design, if you can verify it in the implementation, right? So, like you can see all the nets and left cells, and you can see that all things are implemented perfectly as you need, and that's why that is the interface you'll get. But for a bigger design, it was quite difficult. So for that, we need to use debug probes. So that is the last part. So let's say in simulation, my design is working, but in implementation, my design is not working and my design is huge. So what we can do? So we need to, what I can do, I can see net by net, leaf cell by leaf cell. But these are also only small codes, right? If you are implementing a microprocessor, if you're implementing a microcontroller, a 8-bit microcontroller, so it will have many components. So then this method will be very difficult. So that's why we should know while coding only how to code properly so that the tool will infer that kind of resources. If I'm not confident in my coding, I should use IP code.
Sir,
But
what is
mainly,
IP code?
yeah, those things that is what we'll be doing today in today's session. Okay, and
Sir, sir,
yeah.
one doubt. Sir, leaf cells. What do you mean by leaf cells?
Leaf cells, yeah. So let's say that LUT, when it gets implemented, it will be a leaf cell. So leaf cell is like a resource inside the FPGA. And
Okay,
net, so because you can see in the netlist tab, you are getting nets and leaf cells. So so in the implementation doesn't know which is block RAM, which is all those things. It will see all the design as leaf cells. So it is a LUT based leaf cell that has been utilized. Slice M based LUT, like that it will.
So like the MOX is also a leaf cell, right?
Yes, so everything, yeah, any component, any resource inside the FPGA after implementation, it will be treated as leaf cell.
Yes, sir. Understood. Thank you.
Yes. Okay. Great. Okay. So we'll start with the session, and we'll point out those things in in today's.
Sir, you are not audible.
Okay. Am I audible now?
Yes, sir. Yes, sir.
Yeah. Thank you. So now we stopped at this point. That is distributed RAM memory, right? There we got to know how this calculation came. 256 cross 1 calculation came. So that is the memory contents of a 256 one, that is one slice of an LUT. Like four LUTs are there in the slice, right? In one slice, this much amount of distributed RAM we can make. Now, using that particular RAM, how can I configure two different port? So let's say there is a requirement such that it's a single port RAM. Single port RAM means one address line, one data in line, and one data out line. Correct? So using this data in and data input and output lines, what I can do? So I can do read in one clock cycle, and I can do write in one clock cycle. So that means in one clock cycle, I can do read or write. Correct? So that thing I can make. So this is the most flexible one, and I can make all these different configurations using the single port in one slice. They have calculated and they have given us this many configuration you can make, right? So 32 cross 2 is one slice. 32 cross 4 means if I am using 32 cross 2 means one LUT, slice M LUT. Here 32 cross 4 means two LUTs, correct? So this different kind of permutation combinations using that, you can have different sizes. Then we have dual port, sorry. So dual port will have one read write port and one read only port. You can see this is dual port. It has one read and write port and one read only port. Using that, this many configurations I can make. And the value, and whenever I'm synthesizing that dual port, I'll get as D. So you can try dual port RAM and you can get this many specifications into one slice. If you need more than that, the tool will take multiple slices. It's not that it is not, you cannot take this many, you cannot have, you can say, more than that. As much as you can create, but it will take on multiple slices. Then simple dual port means it has two ports, but one is fixed for write and another is fixed for read. In that, I can have these two configuration. Then we have quad ports. Quad ports are used. Let's say I have memory. I want to I want to transfer the data into three different modules. So then quad ports are utilized. That is one read and write port and three read only ports. So these are the different flavors of the RAM that you can utilize. So this is slice M distributed memory, correct? So what you can do? So I have provided you with this reference book on day 1 in CLB slices. So here we have different kind of distributed memories they have implemented, right? So you can check if they are implementing with this kind of distributed memory, what is the structure. So how many how many LUTs will be required? So you can see 32 cross 2 quad port distributed RAM. So this is how they have given certain specifications of different memory structures that you can create, right? So that is up to you, or like depending upon your requirement, you can create different memories using the reference of this user guide. And I have given a sample code. You can just include multiple ports. You can just increase the address width. You can just increase the data width, and different kinds of distributed RAM will be created. The only thing is that when I'm writing a code for distributed RAM, the write should be synchronous and the read should be asynchronous. This is the only thing that you need to take a note. And I can make the read synchronous. How? By using the slice flip-flops. Correct? Okay. So going to the next point, why we want to make those LUTs as shift registers. That's the main thing, right? So before going to this, I want to take you to this case study. So in this case study, we can have a proper analysis of why why there is a requirement of LUTs that we need to configure as shift register logic, right? Let's do that. So let's say this is my design. This is a design specification. So I'm giving it as 64 bits. So 64-bit data is coming from this point and it is coming out at this point. This is my design, let's say. So this 64-bit data has two parallel paths. This is one path coming to the input of the multiplexer. This is another path which is coming to the input of the multiplexer, right? So two parallel paths are there. In two parallel paths, we are doing the multiple operations, right? So here I am doing 8 cycles of operation in operation, like in this point, that is operation A. Here I am doing 12 clock cycles of operation. So total number of clock cycles after which I will get this 64-bit data is 20 clock cycles. My requirement is this data also should be synchronous, because in FPGAs, in hardware designs, it is always required the data should be synchronous to the clock. So that means I need to synchronize the data at the same speed, right? So, but in this parallel path, we have only 3 clock cycles for operation C. So 17 clock cycles before the data will come. So what I need to do? I need to slow down the data. I need to register the data for 17 clock cycles. Correct? So this is my objective. Now, how to like come up with the solution for that? So 17 clock cycles, I need to stop the data. That means for 17 clock cycles, I need to register it. So 17 number of flip-flops will be used. And how many data bits are there? 64. So 64 cross 17, how many flip-flops will be required? 1088 flip-flops. So for doing only no operation, these flip-flops are not doing anything, just it is registering for multiple clock cycles. So for 1088 flip-flops will be 1088 flip-flops will be required for registering it for 17 clock cycles, 64 bits of data. So 1088 flip-flops, how many slices it will be spread across? So in one flop, how many slices are there? So in one flop, in one slice, how many flops are there? 8, right? So 1088, yeah, 1088 divided by 8, 136 slices will be required. So in 136 slices, this 17 cycles of operation will be spread across. So you can remember, you can understand how many how much routing it will be required, how much placement will be required, right? So this is for implementation with this one. This is for implementation with flip-flops. Let's just change this and make the implementation using shift register logic, right? So one shift register logic, that is using an LUT, can shift up to 32 clock cycles. So one shift register can shift the data up to 32 clock cycles, right? That is shift register LUT. That is slice M LUT can shift the data to 32 clock cycles. That we know. So how many? There is maximum to 32 clock cycles, and all these are dynamic addressing. So dynamic addressing means I can have 10 clock cycle data shift. I can have 12 clock cycle data shift. I can have 20 clock cycle data shift. I can have 25 clock cycle data shift, right? So I can also have 17 clock cycle data shift. These are all dynamic shifting. How? By changing the address lines only, I can make it 17, right? I have 5-bit address line. Using that, I can easily make to 17. But just I need to binary code it, and I need to put here 17, right? So for 1 bit, we need only 1 LUT. So for 64-bit, how many LUTs are required? Only we need 64 LUTs. And in how many slices it will be spread across? This is 64 divided by 4, because in one slice we have 4 LUTs. So it is 16. So in 16 slices, the same operation can be done. So what is the better implementation? 16 slices or 136 slices? 16 slices is the better implementation, right? So for this kind of operation, that is what kind of operation is this? Serial in, serial out. And there is, and in this kind of operation, what I am doing, that inputs and outputs are also synchronous. So synchronous inputs and output. And data is on a pipeline. You can see there is no reset also. No reset. So in such kind of operations, I can easily use LUTs for better implementation. You can see, rather than using 136 slice, I can conclude the work within 16 slices. Right? So that is the advantage. So you can imagine how much performance will be increased, how much area it will be optimized if I use SRL, that is shift register LUTs, for implementing shift register logic. That is serial in, serial out operation. Is this analysis like any queries on this analysis?
Sir, can you again repeat that 16 slide?
Yeah, okay. Okay, fine. So what
Sir,
happens?
please repeat it, sir. Unable to understand.
Okay, fine. So you can see here, this is a design specification. Okay, so as per this design specification, I can use, I want to delay this data by 17 clock cycles. Till this point we know, right? So this 17 clock cycles, what I can do, I can use flip-flops. That is the basic thing, right? If I want to register the data for 17 clock cycles, 64-bit data, blindly will say we'll be using flip-flops. But what happens if I use flip-flops? What happens is, how many flip-flops it will take? So 64-bit data, one flip-flop will be using to register to 1 clock cycle. For 17 clock cycles, what I will be doing? 17 parallel flip-flops. That means 17-bit shift register logic we need. So how many flip-flops will require? 64 into 17, that is 1088. That is spread across 136 slice. This point you understood, everyone?
Yes, sir.
How it is 136?
How many slices? How many flops are there in one? How many flops are there in one slice?
I think 20.
So it is 8. You have discussed that it is 8. 8 sequential elements, right? So 1088 divided by 8 is 136. Is it fine, sir?
Okay, sir.
Yeah. So that means for this operation, my design will be spread across 136 slice. So you can imagine, you have seen the this one, right? You have seen the hardware, the implemented view, right? So across 136 slices, my design will be spread across. So internally, the routing delay will increase, the gate delay will increase, the performance will be very bad. The data will not be in a proper skew. All those things will be coming, right? So I cannot tune the circuit on a higher frequency. And my area consumption also will be very high. So what is the advantage of using shift register LUTs? So here you can see one shift register LUTs can be slice and LUT can be used as 32-bit shift register. So in one LUT itself, I can I can do shifting of 32 bits. So 32 bits you can see here, one LUT can be used as 32-bit shift register, and not only 32-bit. Depending upon the address line, I can make it to any value from 0 to 31. Just I need to change this value here. Correct. So for 1 bit to delay it for 17 clock cycles, I need only one LUT. Correct. So how many LUTs required? 64 LUTs. Is it fine? Is why 64 is required? You got to know?
No, sir.
Is it fine? Shall I repeat?
Sir, up to the 32-bit, like you showed that mux, like
Yeah.
it has five
Yes.
it has
Yes.
five select left. Then like you the next slide, you please go to the switch to the next slide.
Yes, correct.
At the 17 cycles, you wrote one LUT. That I didn't understood.
Yes. So you can see here, I have 64 bits. Here it is 64 bits, right? I need to register 17 cycles. So what I need to do, in each bit, I need to put LUTs, because one LUT can shift up to 32 clock cycles, right? 32-bit shift register. So instead of 32-bit shift register, I can use 17, because 17 is less than 32. So what will happen in this address line? I will put 17. So once I put 17 here, so this data will be shifted by 17 clock cycles, and it will be coming out here. So for 17 clock cycle shift, I need only one LUT. For 64 bits, I need 64 LUTs.
Yes, I understood.
Yeah. Everyone understood that? Okay. So 64 LUTs will be spread across how many slices? In one slice, how many LUTs are there? 4. So 16.
Yes, sir.
Correct. So 16 LUT in 16 slices, the design will be spread across. So which is a better implementation?
So the second one.
Yes. But yes, correct. So shift register LUTs are better implementation in such scenario, but we have to identify what kind of scenario. So now the rules and restrictions will come into the picture. So first thing is that it is serial in, serial out. It is serial in, serial out operation, right? Serially the data is coming, serially the data is going. All 65 data are registered in like one by one. So in, serial out only it will work. If I do parallel implementation, parallel in implementation, it will not work, because you can see here, this LUT, this only one is only connected to the DA input. Correct. So parallel in serial out or parallel in parallel out kind of operation will not work. Only for single serial in, serial out. So if I write a code where I am having parallel in serial out or parallel in parallel out kind of configuration, the tool automatically will infer flip-flops. It will not infer this shift register LUT. So we have to write a code only for serial in, serial out. This is the first thing. What is the next thing that we need to focus on? There is no reset, because if you remember, if you have if I've gone through the user guide, you can see those slice M LUTs has clock, but there is no reset, because of this is how they have made their technology, right? So since there is no reset, what does it mean? If I put reset, that directly the tool will synthesize it to on flip-flops. It will not synthesize it to on LUTs. So in my code, there should not be any reset. The third thing is that all the inputs and outputs should be synchronous. Synchronous means it should come at the time with the clock reference. It should not be asynchronous clock, right? So the input and output should be synchronous. So when I'm coding for shift register LUT, we have to write the code by keeping in mind these 3 points. Otherwise, if you miss any of the 3 points, directly it will synthesize into flip-flops. Is this fine?
Yes, yes.
Yeah. So this is the restriction that we need to understand. So let's do it in a lab and let's try it. So I want to make a 32-bit shift register using shift register LUT. How to code it? So that is what important is, because we should know how to write a code to infer a proper resource. Otherwise, I cannot control the resources. If I cannot control the resources, the performance will be very bad and my timing will get affected. Right? So we'll go to day 2. I have already provided you the lab. This is the lab. This is lab 2. This is the lab that we have missed. Yeah. So here I am launching the tool. Let me launch the tool. I have already provided it here. So we'll do a lab for that. Let's understand it using a lab. So I'll remove this distributed RAM. So this was the previous lab. So I'll add the sources. So add and create design. From there, I need to add a design source, add files. So source code, Verilog. So not that. It is in lab 2, right? I have provided you the template. Verilog. Yeah, shift register LUT. Then click on finish.
Shift register LUT is only for CISO or any other operation? You can
only for CISO. Only for CISO.
We cannot change it into people.
No, because there is no parallel load facility. Only for CISO operation only. Because it will have restrictions, right? So you cannot help it out. Yeah.
Actually, if we make it in people, then I think again it will be reduces time, because in parallel means.
Yeah. But in only for serial in, serial out only you can use shift register logic in LUTs, not for this one, because that's why for 1 bit it can have 32-bit shift. Otherwise, in parallel, if you create, then only for 1 bit it will have 1 bit shift. So again, the implementation will go high. The utilization will go high. Okay. So let's discuss how I have written the code. So how I have inferred this one. So what I told, the first thing is that serial in, serial out. So you can see here serial in, serial out. There is no parallel load. If I include parallel load, that is multiple bit data, automatically data will be, automatically the tool will synthesize it to this one. Automatically the tool will synthesize it to two flip-flops. It cannot synthesize it to shift register LUT. That is LUT, slice M LUT. Then you can see there is no reset. There is no reset here. So there is, even you have seen, right, in that LUT there is no reset condition, like reset connection. So this is how it has been made, right? So we have to follow the restrictions. So if I include reset, everything will go into the flip-flop. Correct? And also this serial in and serial out input should be registered. But here what I have done, I have not registered it. But I am doing 32-bit shift. So what it will do? You can see I am doing 32-bit shift. So here I am using concatenation operator. This input bit is coming to the LSB and the output bit is going to the serial out. What will happen here? This is a basic shift register implementation without clock, without reset. So what will happen is, it will take, since serial in and serial out, we need to register it, it will take 2 flip-flops. And other 30-bit shifting will be done by the shift register LUT. So that means it will take 2 flip-flops and 1 LUT. 2 flip-flops to register the data, input and output data, and 30 for 30 clock cycles, it will take 1 LUT. And you can see in the address line, the binary encoding of the 30 will be there. So this is the analysis. Let's do it practically. So what I'll do?
Can you repeat again, please?
Yeah. So what I told, first thing is that serial in, serial out. This is the first point. Second point is no reset. Third point is the input and output should be synchronous. Synchronous means it should be registered. Here I am doing 32-bit shift. Correct? So this is my 32-bit register that I am declaring. Right? So this register will be implemented inside an LUT. But what will happen? Yeah, this serial in is coming directly, right? This is an asynchronous input. It is not registered. And this serial out is also going directly. You can see it is a it is a continuous operation. Correct? This serial out and serial in are asynchronous. To register it, it will take 2 flip-flops, one for serial in and one for serial out. This point you understood, right?
So repeat again that last 2 points, serial in, serial out, as they are not registered.
Serial in and serial out are asynchronous. Correct? Directly it is coming at any point in time. So this serial in I am providing it inside the shift register, but this is not synchronous. So it should be made synchronous. The tool will make it by how it will make it synchronous? By passing through a flip-flop.
Okay, sir. So it will use 2 flip-flop and 1 LUT.
Yes, 1 LUT, and that LUT, how many bits shifting it will do?
32.
Not 30. Because it is
30. Yes,
30. Yes. Why? Because for serial in and serial out, already I used 2 flip-flops. Again, it will be, what will happen? It will take 34 bits shifting. That is not correct, right? That is not correct as per the behavior of the design, because it has to also follow the behavior of my RTL code. Right?
Yes, width -2.
Correct. So total 32 bit shifting only we will get. But what will happen? In that 32 bit shifting, 2 flip-flop it will be utilized for 2 bit shift, and 30 bit shift will be done by the LUT. So 30 bit shift in using one LUT it can do, because maximum it can do up to 32 bits. Let's do that in hardware. We'll see what happens. So this is the data. This is the LUT. This is the shift register LUT. So I'll click on run synthesis. Click on OK. Just give it a second. Okay, so I'll open the synthesized design. We'll see that is what we should get.
Sir, kindly show here how you are selecting the design, sir.
Yes. So after implementation you can select. So in synthesis, it will be a synthesized netlist. Yeah, let me go to implementation.
Yes.
Yeah. So here you can see already when we are moving into this one synthesis, the synthesis netlist will be created. So synthesis netlist will be divided into nets and leaf cells. You can see here, this is a leaf cell, this is a leaf cell, and this is a leaf cell, right? And these are all nets. So you can see one flop, and this is another flop. Here reset, you can see both the reset are grounded because there is no reset. 2 flops have taken, and you can see this is the shift register LUT, correct? And it is doing 30 bit shift. And see, this is the first bit, this is the last bit, and this is total 30. So total 32 bit shift register I have created in serial out, serial in, serial out fashion only, right? Now what I need to do, I need to run implementation. After implementation only we can see the device view. Why? Because after implementation only this LUT, this shift registers will be placed and routed. Right? Let's do that. Okay. So what you need to do? So first of all, you have to open implemented design. So what it will say we need to close the synthesized netlist. So I'll say yes. So synthesized design will close and implemented design will open. So how will you get to know that implemented design is open? You can see here implemented design is coming. Right? So here sources, netlist and device constant will come. So we need to click on netlist because by selecting the netlist, it will be highlighted onto the device. So we have to click on device here first and we have to click on netlist. So netlist will be the nets and the leaf cells that has been placed and routed. So all the nets and the leaf cells we need to select. So I'll use Control A. So once I got selected, all those things will be highlighted. So on top of that, this thing is there, right? Routing resources. If I disable it, it will give me approximate routing. And if I enable it, it will give me exact routing. So all these two things we need to do. Is it clear, sir?
Yes. Okay. Thank you, sir.
Okay. Now what we need to do is, once it got highlighted, you need to use Control and the scroll button of the mouse. And wherever it got highlighted, I'll just need to zoom it in. So you can see this is one of the flop. Yeah. See, this is the shift register, that is slice M LUT, that is used as shift register, and this is the other flop, right? So this is how the shift register LUT will be implemented. Right? Is it fine? Is it fine till this point?
Yes, sir.
Okay,
Yes.
fine. Okay, thank you. Okay. So now what we have seen as of now. So this is the last, like all the resources we have seen. So we have completed all the CLB resources that are available. So what are the mechanisms that we have utilized to use those things? Now this IB core concept comes into the picture. So here you can see we are using this method, inference. What do you mean by inference is, I'm writing the behavior of the desired circuit using RTL language, that is register transfer level language, right? That is Verilog or VHDL or system Verilog, anything you can use. But what you need to do, you need to describe the behavior here. Depending upon the behavior, the synthesized tool will analyze. That means it will infer and it will use the equivalent circuit using the FPGA resources. So in my code, if I'm using serial in, serial out, without reset and synchronous input and output, the tool will understand that I need to infer shift register LUT, that is slice M LUT. If I'm using reset in the shift register, if I'm using parallel in or serial in, serial out, parallel out, all those configuration, the tool will understand that I need to implement flip-flops. So by understanding the behavior, I am inferring, correct? But let's say I want to implement a memory with many features. Or let's say I want to implement a FIFO memory, fast in, fast out memory, or I want to implement a huge DSP algorithm. So that I don't know exactly what should be the behavior of the proper behavior. So that's why Xilinx has provided us with IP cores. So IP cores means, first of all, what is the full form of IP means? Intellectual property core. So from basic component, from basic adder, subtractor, from basic shift registers to bigger components like Ethernet IPs or memory controller IPs, or you can say memory IPs, or any you can say FFT IPs. All those things are converted as a package. You can say as a block. IP cores means intellectual property cores. It is intellectual property to Xilinx. Xilinx has given us to use the IP. That means I'll use the IP and I will do my designs, but I cannot see what is inside the IP. That is what is the coding of that IP I cannot see. So that will be a black box for me. Even what I can do, I can create my own IPs. I have created my own IP, and I'm putting it for license, and I'm using it for my designs also. So those IPs also I can create and I can use it in my design. Or what I can do, I can buy third-party IPs, and also I can include in my design, depending upon what licenses, all those things, all those flavors are available. So IP core is an intellectual property core from the owner side, right? So those IP cores I can use it for implementing my design faster. Let's say I want to implement a huge memory with more or less features. Let's say I want to implement a FIFO memory. I want to implement, let's say, microprocessor. Already microprocessor IPs are available in the market. I will use those IPs and I will configure it depending upon my requirement, and I will use it in the design. So what is the advantage? I will not wait for someone to I will not like the design time cycle will be quite less, because already IPs are available. I'll connect those IPs. I'll make it my I'll connect to my design, and I will run all my design onto it. Right. So that is the advantage of using IP cores. So when so what Xilinx recommend for small level implementation, we can use inference, but for bigger designs, always it is advisable to use IP cores. Right? You got the concept of IP cores. Now we will be moving on to IP cores eventually. Is it fine? Any clear? Yeah.
Hello, sir.
Yes, sir.
Yes, sir. So whatever the IP core in Xilinx have, right? Just suppose just a PCI DMA, QSFP, Ethernet,
Yes.
a lot of
Yes.
memory, a lot of things. So
Yes,
is it possible to see what inside they have exactly right inside
No.
the?
No. So this IP is, that's why it's called IP core, intellectual property. This is the like to customize. You can customize the IP, but internal parts of the IPs they will not allow to see.
Oh, yeah, because
is
our
not-
interest in that.
No.
Okay.
So that is not possible because this is their like they will not open up the IP and it will show. You can create your own IP. You can lock your IP, but all those IPs are locked. You can
Yeah.
all the information of the IP you can get. What the IP will do, what is the configuration of the IP, all those things will be there. But internal to the IP, it will always be a black box.
Yeah. IP just like a black box, input output is given.
Yeah.
Inside what is happening, nobody knows.
Yeah, means you will have a description of inside what is happening, but you will not be given with the implement like RTL code of it.
Mm-hmm.
They use the same process. They use Verilog only to implement all those IPs, but they will not provide you with the exact level implementation, like or the exact design.
Okay.
Then we have another step. This is instantiation. So all those listers we are seeing, right? We are seeing LUTs. We are seeing those wide multiplexers. All those things, I don't need to do the code also. Directly, I can do interconnection and I can configure it. But this is a very tedious task because I will show you. We'll be doing a IP core example within memory. Same memory instantiation template is like one page. So all those page has at least hundreds of parameters that we need to configure. So that will become very tedious. Like we need to know exactly what is happening inside the block memory. So for that we need to download the block memory data sheet, and each and every bit we need to come up with. So always it is always advisable to use inference for simpler logic. For bigger logic, use IP cores. And for buffers, like I want to implement iBuff, OBuff, for basic things like basic electrical buffers or basic level implementation, only use where the parameters are less, only you use instantiation. So this is the recommendation provided by Xilinx. Is it fine till this point?
Once again, sir.
Yeah. So as of now, what we have done inference. What inference means? I have written a code as per the behavior of the resources, and the synthesis tool inferred that, okay, that means the synthesis tool understood that this, according to the behavior of the Verilog or VHDL language, the RTL language, I have created this particular circuit. This is called inference. There are two other methods. One method is IP cores. That means I will just go to IP core, I will instantiate this IP core, and I will include in my design. Right? So automatically, this is all customized IP cores done by the Xilinx engineers, and those things are logged. I can know what is going on inside the IPs, but I will not able to see the code. Only input and output I can connect. So for bigger designs, always it is recommended to use IP cores. Why? Because it will speed up your design time, right? Then instantiation. Instantiation is another way to use those resources. So you have seen all the leaf cells, all the resources that is available inside the FPGA, I can instantiate, like same as gate level modeling. But what will happen? Those resources will have many inputs and many outputs, many configuration pins. So all those pins you need to configure. So it will be very tedious if the resources is huge. Let's say block memory resources, if I want to instantiate, it will take some time. You have to read the data set. Depending upon the data set, we need to configure. So the tool doesn't, like Xilinx doesn't recommend instantiation for bigger kind of resources. For small resources, it is quite helpful. Let's say I want to implement some clock buffers inside the design. I want to implement certain input output buffers inside the design. Or I want to implement a simple, you can say, electrical high impedance state buffer, that is tri-state buffer into the design. Certain serializer, deserializer, small buffers into the design, electrical buffers that are available. All those things I can use using instantiation. These are the three ways to use all the different FPGA resources in my design. But for, let's say, inference, let's say Xilinx never recommends to implement FIFO memory by writing a code. FIFO means first in, first out memory. Yeah. So if I write a code, Xilinx guarantees that your code will not be 100% proper, because the tool is not intelligent enough to provide the correct resources. So that's why the Xilinx has provided us with FIFO IP cores. Correct? So for high level, like for if I'm implementing a bigger algorithm, or let's say if the IP core is available, then always it is recommended to use IP cores, or you can use multiple IP cores and then you design your algorithm. Is it fine?
So, fine, sir. So can you give an example of instantiation while designing the IP cores?
Yes. We'll do IP cores also, we'll do instantiation also. So as of now, what we have done, only example we have given is inference. Now we'll be moving to IP cores, then we'll be moving to instantiation. One by one, everything will be covered. But instantiation, I will also give you some instantiation template is also there. But for small parameters, for small resources, it is quite easy and it is quite useful. But for bigger parameters like block RAM, bigger resources, it is quite tricky. So that means we have to follow the data set. We have to provide the configuration bits. I'll do that in a visual way that will be more useful. Okay. Is this okay? Yeah. Till this point, any queries?
No, sir.
Okay, fine. So now we'll go to the next resource, that is the dedicated resource. As of now, all these resources are programmable, or you can say configurable resource. That's why configurable logic block. So next resource that we are going to do is, this is the block memory, that is the dedicated resource, right? So we'll see what is the advantage of using this block memory, that is dedicated resources. As I told, why we need dedicated resource, these are pure silicon, will get very high performance compared to implementing my design into LUTs. So first block objective is to understand the block memory resources, right? So this is a dedicated chunk of data that is available, and we'll see what are the features available with that. So whenever, so what they have done, so you can see this 36 kilobits of memory they have provided as silicon inside the FPGA itself. And what is the advantage? You can see all operations are synchronous. Input and output, that is read and write operation, both are synchronous. So whenever I am writing a RTL code where my read and write are synchronous, that is happening on the clock edge, the tool will understand that I'm inferring a block memory. That's why it's called block memory. One block of memory it is given. But what is the disadvantage? If I'm using a 1-bit memory also, it will take a minimum of 18 kilobits of memory. So other only 1 bit will be used, other 18 kilobits of memory it will be wasted. So that's why for bigger memory implementation only it is recommended to use block memory. Internally, I can do pipelining also. If my memory is huge, internal there will be the gate delay will be more. I can do pipelining. I can do registering of it. All the inputs and outputs I can have dual port with independent port access. That means I can have different addresses. I can have different clock, different write enable for individual ports. That is not possible using a distributed RAM because it is a dedicated memory. What the Xilinx has done, this is because it's a physical memory, all those things they have included inside the MFPG to make it like an ASIC-like kind of performance. So it has true dual port, it has simple dual port, it has single port. All those features are available. Correct? Then let's say I want to build a 512 KB of memory. So internally it has integrated cascade logic through which it will cascade multiple block RAMs and it will make a bigger memory. It will not use the programmable resources of the FPGA because it will otherwise it will be slower, right? So it will have dedicated cascade logic to combine multiple block RAMs to make a bigger RAM. Then it is byte write enable. Let's say I want to write A, B, C, D. So each are of 8 bits, right? ASCII coding. So this is my 32-bit data. Out of this 32-bit data, I want to register A, I want to register D. Like I'm only interested to write A and I'm only interested to write D. I am not interested to write B and C. So what I can do? I can use byte write enable method. So what will happen? Each and every byte of the data I can control by this byte write enable. So I can have 1, 0, 0, 1. So this two will be discarded. Only this two data will be written. So in one word, I can write byte by byte. That facility is not available in distributed RAM. Since it is a dedicated RAM, they have included all those features. You can see here, if I am building a block RAM, along with that, there will be read pointer, write pointer, there will be status flags, all those things will be there. So for implementing FIFO, so that dedicated logic already they have provided. So all those IP cores, as I told, it will directly take those logic. If I write a code, for simple logic, I can write a code. For bigger logic, what will happen? It will be spread across LUT and my performance will decrease. Internally, let's say I want to implement 128-bit with data width of memory. I want to implement 256 data width of memory. So what will happen? We need to have certain error correction logic, error detection logic, error correction logic. So that will be also provided. 64-bit, 72-bit Hamming error correction logic are also there.
Sir, repeat the line again. 1 minute, just last line.
Yeah, the last one, right?
Mm.
Yeah. So let's say I want to build a huge memory. So while I'm reading and writing, multiple bytes might go into certain faults, right? Faults. Let's say I'm writing it from a distant source. Like what will happen? because of certain changes, one of my bit can be from 1 to 0. Something certain errors can come up, right? So we have this error correction and error detection logic through which we can see if in my reading and writing time is my bits are changing. So that also integrated. I don't need to code all those things. All those features are there inside the block RAM itself. I just need to select it using an IP code. Is it fine?
Yes, sir. Yes, sir. Okay.
Okay. So this is the block RAM. This is available. We have one chunk of data, that is, we have 36 kilobits of block RAM, and or it can be same block RAM can be divided into 18 kilobits. Two independent 18 kilobits of block RAM or FIFO, right? In the Z board that we are using, we have 140 chunks of 36 kilobits of block RAM in silicon, right? So, but the disadvantage is, let's say I want to implement a small RAM, right? 256 cross 1. It will use minimum of 118 kilobit. It cannot divide than 18 kilobit because it is a dedicated resources. It is configurable, but it is not programmable bit by bit. Correct? So this is the disadvantage, but what is the advantage? I have many features. I want to implement huge memories. Let's say I'm receiving certain data from ADC. So if you remember, you can understand, right? ADCs will have 10-bit, 20-bit resolution ADCs. So 20-bit data will be coming at every clock cycle, and the data will be coming continuously. So I can store the data into a block RAM. That is, and in such kind of scenarios, block RAM are quite advantageous, right? So we have similarly, we have single port block RAM. You can see this is one port through which I can do read on write. Similarly, we have simple dual port. Simple dual port is like, these are the three configurations I can use. So this port is for write, this port is for read. Simple dual port separates it. The most important thing that we'll be regularly using is this true dual port RAM. Why? Because here both the clock is asynchronous. So this is kind of RAM where both the port will both this port will work with two different memory implementation. Correct? Both the ports will work with two different memory implementation. Let's say two different clocks, clock A and clock B, but it will work on the same memory. So why it is advantageous? Let's say I'm sending data in 100 clock, 100 megahertz. That means I'm writing the data in 100 megahertz, and here I have a device which is connected. It's a slow device. It has 5 megahertz. So I need to have an asynchronous FIFO so that the data will be transferred properly. Because if I directly transfer 100 megahertz data to a 5 megahertz device, most of the data will get lost. That is not correct implementation. So internally we have to have asynchronous FIFOs. So this true dual port block RAM is the base level, is the heart of the asynchronous FIFO. What asynchronous FIFO will do? First of all, it will write the data onto its dual port block memory in 100 megahertz, and then it will send the data at 500 megahertz. That means it will read the data at 5 megahertz. So what will happen? Properly data without any mismatch, without any metastability, the data will be received. Otherwise, directly if I send high speed data to a low speed peripheral, most of the data will get lost, and or it will I will not have proper design implementation on that. So that's why true dual port block RAM is quite utilized, because it has two different clocks. It can run in two different clocks on the same memory, and it has multiple different those two different ports, where those two ports are independent to each other. Correct? So what does it mean? So I can write 64 bits and I can read 8-bit, 8-bit, 8-bit like that. I can write 8-bit data, but I can read a 32-bit word, or I can read a 64-bit word, because both with the port widths are different. So in different ways I can implement it. So this is very useful when I'm transmitting data from one clock domain to another clock domain. Else, without asynchronous FIFOs, I cannot transfer data from one clock domain to another clock domain because it will raise into metastability condition. The data will miss. So this will be like the buffer inside it. So that is the advantage. These are the 3 ways I can use those block RAM. So those block RAMs also, we have more specifications, like more features. How I am writing onto the block RAM. With that they have 3 configurable modes. We have write first, we have read first, we have no change. So write first mode, you can see here. In write first mode, the data is written onto the DIA and it is available onto the DOA. So whatever data I will write onto the memory, at that instant only it will be available on the output. This is write first. What is read first? Read first means whenever I am writing, at that time if I am reading, the old contents of the memory I will get. We'll discuss this with this one. We'll discuss this using waveforms. And then we have no change. No change is like power saver. Whenever I'm writing the data, the output will be latched. We'll see that in terms of timing diagram. Okay, so if I configure any port as write first, what will happen? You can say this is write enable is high. At this stage, the write enable is high. This is the data I want to write it onto this particular memory location. So this data will be written here at that instant only. But in the output also, I will see the same data at that instant. That is the advantage of write first, because generally what will happen in a RAM, the data will be coming after one clock cycle because it will be taking time to store. Then in the next clock cycle, the data will be coming out. But using this write first mode, I can do that. Correct? So this is a transfer mode. If I want to provide fast, without any clock cycle latency, I want to transfer the data, I'll be using write first mode. But it will consume more power because more switching will happen because data is writing onto the memory and also it is going out of the memory, right? At the same clock age, right? Is this point clear? Shall I repeat it again?
Please sir, repeat it, sir.
Yeah, because this is important. Okay. So when the memory will be able to write, whenever write enable is high, right? So you can see here write enable is high in this point and write enable is high in this point. In other points, it is only read operation here, here and here. So what it will do, it is only reading. Right? So whenever the I'm doing write enable, you can see here I'm using write enable signal. That means the write enable is high. I'm sending this particular data. If I'm sending this particular data, what is happening? In this particular address, this data is writing. Right? The data has been written. But at that instant only, after some intrinsic delay, that is inside gate delays, I'm getting the output at that moment only. So this is the advantage. Generally, what will happen? It will take one clock cycle. The new data will come at this point. But here, at that instant only, when I'm writing the data, I'm getting the data at that moment only. So this is the write first mode. This is a transfer mode. Yeah.
So you are saying for dual port block RAM?
No. It is for all single port, for simple dual port, for true dual port. For all those RAM, there will be ports, right? Those ports can be configured as write first, read first, or no change. So any of the port inside the single ports, simple dual port or true dual port can be configured as write first mode.
Okay, so conclusion is this: so either it is simple port or simple dual port or true dual. At a time we cannot read write. Whenever we are writing, second port should be in waiting.
No. In a memory, whenever in a generalized memory, whenever I'm writing, I will not get the output that memory contains at that instant. I need to wait for one clock cycle. But yes, correct. So in a generic memory, but in block RAM, in any of this configuration, in case of block RAM, Xilinx block RAM, in this configuration, using this write first mode, I can make the data coming out at that clock instant only, because that particular port is working in write. It can be single port, it can be true dual port, it can be simple dual port, but that particular port can be configured as write first mode.
Yes, sir.
Fine? Yeah. Similarly, you can see read first. So read first is that the previous, like the generic one. So I don't need like the data. I don't need the data to be transparent. That means I don't need the data is coming at that clock cycle only. I can wait for one clock cycle. So what I can do, I can use read first mode. So the previously stored data will be coming, but in the next clock cycle, the new data will be coming here. So this is read first. Similarly, no change. No change is like this mode where whenever the write enable is high, the output will latch. You can see the output has been latched. So what will happen? There will be no switching. If there is no switching, there will be no dynamic power dissipation. If there is no dynamic power dissipation, only static power dissipation will be there on the read port. The power consumption will be quite less. Correct? So that is the advantage of no change mode. So this no change read first and write first mode, I can directly write a code and the tool can configure, right? So let's understand how to quickly, we will try to understand how to come up with write first mode and also how to come up with an IP code, right? Quickly we'll do that. So I'll go to day 2, in day 2 lab, I will create a lab here. In this lab, I will launch the Vivado tool. So what I have given for a single port memory, all those different configurable block, like configuration, that is write first, read first, and no change, I have written a code. So I will give you demonstration of the write first mode. You can also take up and you can also see the read first. You can also see how no change we have done. All those things we can do. So what I will do, there are total four codes. I will give you demonstration on the read first and how to use the IP code. Other things you can analyze, or if you have any doubts, what we can do, we can discuss on the on tomorrow or day after tomorrow session. Okay. So I'll create the project quickly. The process will be the same. Next, because write first is quite important. So we'll see how to write a code for write first logic. So the project is memlab. Click on next. Click on the boards. Then this is the board, Avnet Jetboard I am using. So this is RTX 7 FPGA. Click on finish. So the project has been created. So first of all, I'll add the source, then we'll explain the code. So I have added the design source. I'll go to source code, Verilog. This is the write first mode that I have selected. We'll discuss the code. First, we'll try to add it. Now we'll discuss. So this is the write first code, right? Also, I have provided the test bench so that you can run the test bench and you can see the behavior. So you can see this is the same 256x8 memory allocation, but here what I have done, this is a block RAM with write first mode. That means the read and write are synchronous. So what I have done, when the data is been writing, it will do read operation also. So both those operations I have I have provided inside the write enable. So whenever the write enable is high, the data will be written to the memory. Also, the data will be read out of the memory. Both those two statement will be executed parallelly. Why? Because I am using non-blocking assignment. Correct? If the write enable is low, only read operation will happen. Write operation will not happen. So just by writing 4 lines of a code, I can tell the tool that I'm inferring a write first block memory. Is the code clear?
Yes, sir.
Yeah. So let's see. Like once I am writing the code, what I need to do, I need to synthesize. So once I will synthesize, what should come? First of all, it should not come in LUT. This is the first thing. Second thing, it should come a block. One block of RAM should come, and it should be minimum of 18 kilobit. It cannot be less than 18 kilobit. So in 18 kilobit of block RAM, only 256 cross 8 memory will be implemented. Let's see that. We'll synthesize it. We'll understand it. Then that particular port that we have configured should be of write first mode. Three things we need to identify. It's synthesizing. Please give it a minute. Okay. Open synthesize design. Click on OK. Yeah. So you can see one block of one chunk of memory is coming. You can see this is a block RAM of 18. 18 means it is an 18 kilobit of block RAM. So here from this 15 bits, all those ports are available, but it has configured it into a single port memory only. So in one clock cycle, I can read or write. Out of that, 8 bits are for the output. You can see here 8 bits are for the address lines and 8 bits are for the data lines. Other things are been connected to 0, right? So one chunk of block RAM memory is coming. So if I select this particular memory and I go to the cell properties, if I go to properties here, you can see this is a block memory here, and you can see this the first port will be the single port memory. So here this is configured as write first mode. By the coding itself, the tool understood that I am configuring it as a write first mode. So what we can do, we can just run the I've already provided you the test bench. You know how to use the test bench well. So just run the test bench and you can see what you can see the data and the output is coming at the same time. You just do it. Tomorrow, if any queries, we'll discuss about it. Fine. So quickly, what we'll do? Yeah. Yes, sir. Any queries? Okay. So this is by writing a code. Now, what is the disadvantage here? Because I need to know the behavior of the block memory. After understanding the behavior, I have to write a proper code. So for simple things, it is fine. For bigger things, it will be difficult, right? So always we have the help of IP cores. So I'll just remove this from particular project. I need to add a block RAM IP with a single port block RAM with write first mode using IP. What I will do, I'll just go to IP catalog. You can see IP catalog is basically the library of all the IPs that are provided. Same thing, without writing any code, I will configure it. So what I will do here, so I'll write block memory generator. You can see block memory generator came. So I'll double click on that. So once I have double click, you can see this is a single port RAM, and it is not AXI based port. It is only a native port, and this is the block RAM that I am generating, and it is single port, and it is 256 cross 8. So this is the name of the component that I have created. Okay. So you can see here, this is port A option. It is of 8 bits. And the depth, what we have given, the depth is 256, right? 0 to 255 means 256 that I have created. So that I have created. So here you can see directly I have given it, automatically it is configuring. The IP is configuring. Here I can select any of the operating mode, read first, no change, anything. I don't need to bother about the coding. Here I don't need any output. So if I want to register the output, I can click here and automatically flip-flops will be inferred. It will, if I use this, internal flip-flops will be inferred. If I use this, external flip-flops will be inferred. I can just click here, one reset pin also will be coming here, right? All those options we have. So other options, I want to initialize the block RAM with some values, because generally it starts with X, right? So I want to initialize it. Directly I can put some COE file. COE file is like a text file where at each and every address I will be providing certain data. That data will be going to inside the block memory to initialize it. So those facilities are available. If I want to initialize that memory in the Verilog code, what I need to do, I need to write it on each and every memory at the reset stage. So that will be very tedious, right? So I can directly use this COE file. Then you can see the summary. It will take 1 kilobit of block RAM. Then I will click on OK. So without writing a code, I have generated this IP code. So it will ask to generate the particular IP code. I will click on generate.
So from where we can get COE file?
Yeah, COE file we have to make. So I'll let you know how to make the COE file. COE file is the coefficient file.
Yes.
So COE file is a basic text file only. Yeah, 1 second. So you can see in design runs, this block memory, you can see this block memory, what it is synthesizing. It's synthesizing separately as an IP. So let us synthesize. We'll understand how to make the COE. So what I have done in COE, you can see, I have initialized, I have written it this. So COE file also, this format also I have given. For any kind of COE file, the format will be same. First thing. The second thing is that you can see here memory initialization radix. This is the command. So this is 10. 10 means it is binary number system, unsigned binary number system. Unsigned decimal number system. And this is the memory initialization vector equal to. So this means it is for address 0 here. In address 0, 1 will be there. In address 2, 2 will be written. In address 3, 3 will be written. In address 4, 4 will be written. In address 5, 5 will be written. Like that, all the, just I am giving, just it's a basic example. So all the sequential data I am providing here, and it will go up to 255. So how many, so if I am creating a memory of 1024, how many values I need to provide? I need to provide 1024 or any kind of less than 1024 values, but it should not extend beyond 1024, because then it will be an error. So anything less than 1024 also it will work, because what it will do, all the uninitialized state will be initialized as zeros. So this is the same kind of format you need to create for any kind of COE file. Is it fine, sir?
Yes, sir.
Okay. So that we have provided, the RAM is generating. So this is an IP core. To synthesize it, to implement it, I need a wrapper. Wrapper is like a top module which will wrap this IP core like a module instantiation. So that I will add. So in this wrapper, what will have? It will have only input and output definition. You can see this is the RAM IP core. It will have only input and output definition. Then click on finish. So I am including the wrapper first. So this step is important. I have configured the IP. Now I want to add it inside the RTL code, right? So first I will remove this and save it. Then I will show what is there. So all the input and outputs are there in like at the module. Only I have declared input and output, and there is nothing else. You can see here, there is nothing, no code here. So here what I'll do, we know instantiation, right? We know named instantiation. Using named instantiation, I will connect the wrapper with the IP code. That is what we will be doing, right? So what I'll so what to do that? How to do that? So I'll go to IP sources. You can see here, I'll go to IP sources. I'll click here. This instantiation template is the output file that is generated. You can see some synthesis files, some simulation files are also generated. I will select VEO. VEO is the format for the instantiation template in Verilog format. VHO is in the VHDL format. So I am not doing VHDL, I am doing Verilog. So I will copy this. So this will be generated for any of the IP cores you are creating. So that IP core instantiation format I will paste here. Then here I will write the instant name. So this is block memory 256 cross 8 that I have provided. Then I have to provide clock. So that clock I have provided here. Then I'm doing the connections. This RAM enable I have provided here. This write enable I am providing here. So I'm doing just the connections here. The address I am providing here. Then data I am providing here. Then data out I am providing here. So all those things I have provided. So input and output, everything I have provided, and I will save it. So once I save it, you can see it is updating. The hierarchy is updating. So this memory, block memory, will go inside the top module. That is the wrapper. Correct? So this is done. So what I will do, I will just run synthesis. So once I run synthesis, you can see that particular block memory got synthesized. Just give it a minute. Just last point. I will just run synthesis and we'll see the results and we can conclude for the day. With running synthesis, please wait. Just give. Yeah, you can see the synthesis has been done. So I'll open the synthesized design. So what is the output that we need to see? We need to see a block RAM only, correct? But here it will be, the representation will be different because IP, it has been packaged. So there will be multiple layers. So at the time of implementation, those layers will be naviggated. But here, since it is an IP, it will have multiple layers. So just I will extract those layers because it has those because it is included as an IP. This is the same block RAM, but it has multiple layers. So these are only, you can say, non-synthesizable layers. This is like because the IP has been packaged. So those layers are coming at the implementation level. Those layers will be naviggated. This is not a synthesizable subset, you can say, but internally inside those package, we are seeing the same block RAM memory. So this is how we can create memory using IP cores, right? So we'll stop here because we'll not go extend it. So in the next subsequent videos, like subsequent discussions, we'll be using those IP cores, we'll be using those RTL code, we'll be using synthesis and implementation, we'll be generating the bitstream, and then we'll be programming the FPGA through cloud access, that is through remote. That will be the next objective. Okay. So any queries till this point, please let me know.
Sir, can you please share the recording?
Yeah, today only I will share. Yesterday also I have shared, right? So today only, just now I will be sharing it. Is it fine? Okay. Just you practice this once. If any queries, we can take all those things because there are many things. Read first and no change. All those things you need.
Today, the topics that would cover today was very new for me. So I have to revise once again.
Okay, yeah. You just go through it, and if any queries, we'll create we'll have a session on those queries first. Is it fine, Abhinav?
Okay, sir.
Okay. Thanks. So any other doubts?
No, sir.
Okay, fine. So we'll stop here. So we'll take we'll continue the session tomorrow same time. Thank you.
Thank you, sir.
Thank you.